Welcome to this video. Today we are going to see Ethernet. There are two versions basically based on how it is. One is classical Ethernet that basically tackles the problem of multiple access to the shared channel with the help of the MAC sublayer protocol. It runs with a speed of 3 to 10 Mbps and runs in the physical layer. Next is the switched Ethernet, basically which connects the multiple system to each other using the devices called as switches. We'll see what they are. So it has got the speeds of 100 Mbps up to 10,000 Mbps, categorized as fast Ethernet 100 Mbps, Gigabit Ethernet 1000 Mbps, and 10 Gigabit Ethernet 10,000 Mbps. So we'll see first the classical Ethernet. Here the researchers Bob McAfee with David Bogus designed and implemented the first LAN in Xerox Palo Alto lab in 1976. Basically they combined or they connected the machines using a single long thick coaxial cable which gave a speed of 3 Mbps. Now the Ethernet basically was called as luminiferous ether that time, because when Maxwell devised the electromagnetic waves, at that time scientists assumed that the waves were transmitted through the atmosphere through us, for example, using a medium, and so that the space was filled with some medium, and that medium was called as luminiferous ether. It was after that it was researched and found out that waves can even transmit in vacuum. So that's a conceptual matter only. Ethernet, the name Ethernet is after the luminiferous ether, which was a concept used that time. Now it was successfully designed so that the standard was also drafted by Xerox, DEC, and Intel with 10 Mbps in 1978. In 1983, it became the IEEE standard, IEEE 802.3. So this is the name. Ethernet is also referring to the same technology, and IEEE 802.3 basically a standard that defines what that Ethernet is. So there is a subtle difference, but most of the times Ethernet and IEEE 802.3 are used interchangeably. Now the classical Ethernet can be of two types based on the cables and used there. First is thick Ethernet and second is thin Ethernet. The basic differences were the thick Ethernet use a thick cable, that's why the name, and thin Ethernet obviously use a thin cable and connected the machines using BNC connectors. In the case of thick Ethernet, the wire or the segment could be as long as 500 meters, where that in the case of thin Ethernet was only longer up to 185 meters. So that was only 185 meters at the maximum, whereas that was there in the case of thick Ethernet could be as long as 500 meters. Now in the case of thick Ethernet, there could have been at max 100 computers connected. In the case of thin, the maximum number of computers connected was 30 only. So these are the differences between the two. Now when the computers were more longer than the maximum cabling length specified here, they were required to be connected. So more than 500 meters or more than 185 meters, you can say. So that connectivity was possible with the devices called as repeaters, which is a physical layer device that receives signals, amplifies those signals, and retransmits those signals in both the direction, in the received as well as where it was to be transmitted. So this is the architecture of the classical Ethernet, wherein you can see a cable which is running along, and that is called as ether here, and to that cable there are multiple transceivers connected. Transceivers means which can receive the signals and transmit the signals, transmit and receive, so transceivers. So they using those transceivers, multiple computers were connected to that Ethernet. That's a basic architecture, and those cables basically used Manchester encoding. Here the restriction was that no two transceivers could be more than 2.5 kilometers apart, like this, as you can see here. So no two transceivers could be more than 2.5 kilometers apart, and that too, no path between any two transceivers could traverse more than 4 repeaters here. For example, we know that the repeaters were used to increase the length for connectivity, but those restrictions were there. So no two transceivers could be more than 2.5 kilometers apart, and that too with the maximum repeaters allowed within them is 4. This is because of the MAC protocol used there, that the limitation was necessary. Now we'll see the frame formats which are used for the Ethernet for sending and receiving frames. So what you can see in figure A is applicable to the Ethernet. As we have just seen, though Ethernet and IEEE 802.3 are used to refer the same thing, or used interchangeably rather, there is a subtle difference that can be seen here. So this is the Ethernet frame format, and this is the IEEE 802.3 frame format. So the first thing is the preamble. So the preamble basically has got 8 bytes, out of which 7 bytes were of format 10101010, and the last byte of format 10101011. That means the last 2 bits were only changed from 10 to 11, and that 11 indicated start of the actual frame, and that's why it is called a start of frame delimiter in 802.3 SOF. Here the Manchester encoding of this particular pattern produces a 10 megahertz square wave for 6.4 microseconds, so that the sender and receiver can synchronize themselves. And once the bit pattern 11 starts, the receiver and the sender knows that, I mean the receiver knows that there will be a start of the actual frame. Now as you can see, after that preamble there comes the destination address of 6 bytes and source address of 6 bytes. So basically these are the addresses which are used to designate the destination machine and the obviously source machine. Here 3 types of addressing is used. First is called as unicasting, which is used to refer to a single machine. So that is called as unicasting. Here in the case of unicasting, that is used to refer to a particular single machine on the network. The address is special, in which the first bit of the destination address is 0 for ordinary or the unicasting address. Whereas in the case of multicasting, that is used to refer to a group of machines. The first bit of the destination address is 1. The difference between unicasting and multicasting is that in the case of unicasting, it refers to a single machine, where multicasting address will refer to a group of machine. Now this multicasting allows multiple destination to listen to a single address, as we have just seen. but that needs to have group uh, mechanism. Group management is required there. So the next or the third category is broadcasting, where that special address which has got its all bits set as 1. That means whenever that address is used, the corresponding frame having its destination address set to all ones will be transmitted to all the machines. That is called as broadcasting. The difference between multicasting and broadcasting is that broadcasting is used to refer to all machines, where multicasting is used to refer to a subset of machines. Here broadcasting, as it is required to be transmitted to all the machines, there is no concept of group because all the machines will be used. So no group management is required as in multicasting. Now the peculiarity of the station source address, of which is of 6 byte, is that, as you can see here, the destination is 6 bytes and source is also 6 bytes. So it is globally unique, which is assigned centrally by the IEEE. Now the concept was that with that unique address, any machine can be identified uniquely, which is spread, which can be there anywhere in the globe. Here, out of the 6 bytes, the first 3 bytes are used for the OUI, organizationally unique identifier, where each of the manufacturer of the computers will be assigned a unique identifier with those 3 bytes. So blocks of 3 bytes, that means 224 addresses. Why 224 addresses? So out of 3, 2 raised to each byte will be having 8 bits, so 3 bytes will be having 24 bits. So this is rather 2 raised to 24. This is not 224. So as there are 24 bits, so in all 2 raised to 24 addresses were possible, and those manufacturers were assigned one of those 2 raised to 24 addresses. So that will be one manufacturer will be having exactly one address out of those those 2 raised to 24 addresses possible, and that manufacturer will assign the last 3 bytes of the address and programs the complete address into the NIC. That means out of the 6 bytes of address, the first 3 bytes will be fixed for the manufacturer, and that manufacturer will assign its own addresses. That means it will select the last 3 bytes for addresses which is assigned by it. So whatever machines it manufactures, for each of that it will be assigning one of the 2 raised to 24 addresses. So in this way, the first 3 bytes will be manufacturer address and last 3 bytes will be the address assigned by the manufacturer. So that all will be combined together as the source address or destination address. So in this way, the MAC address is unique. The next is type or length field. As we can see here, in the case of Ethernet, it is called as type, which is of 2 bytes, and length is also of 2 bytes, which is used in IEEE 802.3. So in the case of Ethernet, it is used as type field. Now the frame, there could be multiple protocols running at the same time on the same machine. So whenever a frame arrives, the operating system has to know which protocol this frame is to be given to. So that requires the frame type to be identified, and for this purpose the type field is used. For example, a value called as hexadecimal 0800, that indicates a frame of IP version 4 packet. That frame is containing one IP version 4 packet, for example. So that is based on the value in the type field. So if it is IP version 4, so it will be given to the IP protocol, for example. So based on that, the type field, the corresponding protocol process will be given that particular arriving frame. So for each of the protocol, there may be different process running in the system, and to that process, the arriving frame will be given based on the type. Now, 802.3 uses this particular same field as length, not type. So the frame length will be put here in this field. And to calculate the frame length, the contents, that is the data contained in the frame, is to be looked. The Ethernet length was determined by looking inside the data in the frame. That is what is called as the layer violation. Because as we know, a corresponding layer only sees its own headers and trailers, not the data part. Whereas this was the length part was taken by checking the payload. That was the layer violation. Now, as this particular field is used as length, there is no way for the receiver to know what is the type of that frame, and that's why one more header was added to the data part for the logical link control LLC protocol. It uses the 8 bytes to convey the 2 bytes of protocol type information. As we have seen previously, the type field was having 2 bytes. Here now 8 bytes will be used to convey the value of 2 bytes of type. Now, a basic rule is that if any number is just to differentiate between the length and type, if any number in that particular field of 2 bytes is greater than hexadecimal 600, it can be interpreted as type, or if it is less than 600, it can be interpreted as length. The next is a data field. As you can see here, after type there is data, which can be from up to 1500 bytes. Now the minimum length that is possible is 64 bytes for the data, and the maximum was possible 1500 bytes. Now that particular minimum of 64 bytes, as you can see here, the frame is from destination address to checksum. So minimum length possible was 64 bytes of that frame. So that's why if you consider the constant values of frame portions, there are 6 bytes of destination address, 6 bytes of source address, 2 bytes of type or length. Then there are 4 bytes of checksum. They are fixed. So in all, 6 plus 6 plus 6, 2 and 4. So 18 bytes are fixed. So to be a minimum of 64 bytes, if the data is less than 46 bytes, a padding field is used. So that padding will be assigned or added to the data, so that this particular portion, from this to this, it becomes minimum 46 bytes. So combined with the destination address, source address, type and checksum, the overall length becomes at least 64 bytes. Now there is a reason why this particular minimum length was used. It prevents the sender to complete transmission before the first bit arrives at the destination. Now why it is required, we'll see with this diagram. Now imagine these are the two machines, A and B, which are there on that Ethernet. where A is the sender that transmit at time 0. A frame is transmitted at time 0. Now it arrives at the distant location B at now, for example, let us also imagine that the time it requires to transmit the whole frame from A to B is tau. So at just before that tau time, for example at time tau minus epsilon, the frame is just about to reach B, and at that time B, as it has not B has also started its transmission. Obviously the collision is there at time t. Now once B detects that collision, it will generate a noise burst of 48 bits to signal all the other stations that there has been a collision and do not transmit your frames. Now as you have seen previously, the transmission time is tau. So for that noise burst which is there, will also take a time of tau to reach to A. Now this is the time which is added to the previous transmission of frame of tau. That's why this noise burst, which is because of the collision of the frame which was transmitted previously at time tau, so that noise burst will require a time of collectively tau plus tau, that is 2 tau. That means the frame was requiring a time of tau here to reach near about B, and when the collision occurred, it the noise burst took once again a time of tau to reach back to A. So in all, A will come to know of the collision almost about a time 2 tau, at time 2 tau. So the idea here is that before completing the transmission of the complete frame, the sender must know that it has been successfully transmitted or collided. Basically the collision has to be known by the sender before the complete transmission of the frame is done from it. So to calculate what that time will be required, 10 Mbps LAN with a maximum length provided of 2.5 kilometers, and a possible maximum repeaters are 4. For this configuration, the round trip time has been determined to be nearly 50 microseconds in the worst case. So the shortest allowed frame must take at least this long time to transmit, obviously, because that is the worst case scenario possible. Now at this configuration, that is at 10 Mbps bandwidth, a single bit will take 100 nanoseconds to reach the other side, and its acknowledgement, the round trip time for that single bit will be 100 nanoseconds, so that the bit takes to the other end and its acknowledgement can be received by the sender. So 500 bits are required to to generate or to withstand or to use the 50 microseconds time. For example, if single bit takes 100 nanoseconds, there should be 500 bits, because 10 Mbps into 100 nanoseconds for one single bit will be calculated to be 500 bits. Now as there are 500 bits, they are rounded up to the next complete bit size, that is 512 bits, that gives about 64 bytes. So that's why the minimum length of 64 bytes was required in the case of this MAC sublayer protocol. So if the frame is at least this long, the sender is not finishing that frame until it has started arriving at the farthest destination. So in that duration, if there is some collision, sender will first know that the collision has occurred, and it will not wrongly assume that the frame has been successfully transmitted. Otherwise, the frame may be incorrectly taken to be successfully transmitted. And the last field that is there is the checksum of 4 bytes. That is the usual CRC field, as we have seen previously in the CRC mechanism. It's a 32-bit CRC where the CRC mechanism was seen previously, and in which we have seen that it's an error detecting code that uses various polynomials, out of which a 32-bit polynomial is used here. It defines a generator polynomial, which we have seen at that time. So with that, we now finish what is called as the classical Ethernet. Now we'll go to see what is called as a switch Ethernet. Here, a drastic change was there. Rather than having a single Ethernet cable, a wiring pattern was changed from a long cable to a more complex architectures, where the stations, each of the station was having a dedicated cable running to what a central device called as hub, as can be seen here. So for each of the device, there'll be a cable that is connected to what is called as the hub with the ports in the hub. Now this is why adding and removing a station became much easier. Now the cable length was only reduced to 100 meters for the telephone twisted pair wires, and 200 meters if Cat5 cable was used. Basically, we have seen that hubs and switches are different. Hubs do not increase the capacity. Whatever that was the collective capacity, that will be shared between or among the available machines or the stations. That's why using hub is equivalent to using the single long cable of classic Ethernet. And that is the reason, as the bandwidth will be shared among the available station, when multiple stations were added, the performance of each station degraded because the bandwidth was shared among them. So this is with the hub. Now the alternate way is to use a switch, where there is a fast backplane, and the outer view scenario will be similar as we can see in the hub. There will be a line or cable running from each machine up to the switch, that is once again connected with the RJ45 connectors to the ports of the device. But inside the switch, the scenario is different. Here whatever the signal arrives, that will be retransmitted to all the ports. But in the case of switch that we have seen, which is more intelligent than hub, that it identifies the destination address in the frame, and this is how only transmit the frame to where it was destined. So that frame will now not be available on all the lines, will only be transmitted to the line or to the machine where it was rather to be routed to. That is the difference. And that's why now the bandwidth is not shared amongst all. The bandwidth is given to the same bandwidth is available to each of the machines individually. That is the difference between using hub and switch. That's why the efficiency and performance is more in switch. Now the problem of that hub could have been solved in this way by increasing the speed from 1 Mbps to 10 Mbps, 100 Mbps, or even 1 Gbps. But whatever speed was increased, the bandwidth was increased. There were applications like multimedia applications. They were also requiring multiple, or you can say higher bandwidths. So just increasing the bandwidth was not the solution. Rather, as you have seen just now, switch was the solution. However, increase was there in the overall bandwidth that was to be shared in the case of hub, and that's why somewhere there could have been some bottleneck or saturation, where the switch does not share the bandwidth among all the devices. It rather gives the whole bandwidth to a single device. That's why switch was the solution. Now, as you have seen, it knows the destination. That's why the packet or the frame will be given to a particular address, a particular machine where it is to be forwarded or to be destined. The other benefits was security. Previously, in the case of hub, we have seen that the arriving frame will be given to all the machines. This is how the nodes which were not supposed to access that frame, it was possible for these nodes to access that. So there was no security. Now in the case of switch, only the machine to which the frame was to be given, that machine was having the capability to access, because the frame was being diverted on that specific line. That's why the security benefits were there. And as if the line used for connecting the machine is full duplex, that means bidirectional communication is possible, there was no possibility of collision of the frame. Collisions could only occur if the cable was half duplex. Now the overall scenario when switch is used is as shown here. The multiple machines could be connected using the cables to the switch using the RJ45 ports. And as like individual machines, even a hub can also be connected to one of the ports, where the hub next having connections to multiple machines, where a signal arriving at hub will be competing to reach the switch, and once it reaches the switch will identify where the destination is. Accordingly, it will transmit. If the destination happened to be one of the machines on the hub, the switch knows that while the frame was coming, it was already broadcast to the remaining machines. That's why if the destination is one of the machines on the hub, the switch will simply discard that, because the frame has already been given to those machines or that machine. Now, depending on the cabling technology, now basically as the applications evolved, the bandwidth requirement was more and more, so the fast speed was required, and that was available with the changes in the cabling technology. As can be seen here, we are seeing three such technologies. One is 100 base T4, which is using the twisted pair, which is of category 3, unshielded twisted pair. The maximum segment length could be 100 meters. The next version, called as 100 base TX, is also a twisted pair technology with the same maximum segment length of 100 meters, but it is full duplex at 100 Mbps. The previous technology did not support 100 Mbps at the 100 meters. So the speed is increased here with the help of category 5 unshielded twisted pair. And the last technology or cabling technology, you can say, is the fiber optics used, which is called as 100 base FX, F for fiber, which could have a maximum segment length of 2 kilometers with full duplex at 100 Mbps with the increased length. Now, after some time, as the speed for even more the requirement for even more bandwidth was there, the graduation toward Gigabit Ethernet took place. And the goals for that was increased performance, almost about 10-fold over the fast Ethernet that you have seen just now. But it was to have backward compatibility with both classical as well as fast Ethernet. It was to support unacknowledged datagram service with both unicast and broadcast. It has to use the same 48-bit addressing scheme just you've seen, and it has to use the same frame format, including the minimum and maximum constraints, we can say, size constraints. Here there could have been multiple arrangement. The simplest one is the just two computers connected using the Ethernet, or there could be multiple stations connected using either switch or hub. Now the based on cabling technology, once again, as we have just seen in the fast Ethernet, there are some technologies used here in the Gigabit Ethernet cabling. So 1000 base SX and LX both are fiber optics, where SX runs for 50 meters and LX runs for 5 kilometers, the maximum segment length. In the case of 1000 base SX, a multi-mode fiber of diameter 62.5 microns is used. In the case of 100 base LX, a single 10 microns fiber or multi-mode fibers of 62.5 microns is used. The other technology, cabling technology, is twisted pair, where 1000 base CX has got two pairs of shielded twisted pair, which can run only up to 25 meters. The maximum segment length can be only 25 meters. It has got shielded twisted pair is used here. The other technology, 1000 base T, uses 4 pairs of UTP, which can go up to 100 meters, which is standard category 5 UTP, unshielded twisted pair. Now, when even more speed or bandwidth was required, the technology was further changed with 10 Gbps speed, 10G base SR, 10G base LR, and 10G base ER, all of them employing the fiber optics, which can go respectively from up to 300 meters, 10 kilometers, and 40 kilometers. In the case of SR, the multimode fiber of diameter 0.85 microns is used. In the case of LR, a single mode fiber, LR and ER both employ single mode fiber of 1.3 microns, whereas the remaining two use the twin axial. The 10G base CX4 employs 4 pairs of twin axial cable, which can go up to only 15 meters, and the last 10G base T, 4 pairs of unshielded twisted pairs is used, which can go, the maximum segment length can be 100 meters, where Cat6 cable is used, category 6A UTP. So at the last, we'll see the different devices and at what layer they are used. Previously, we have seen repeater and hub. So these are the devices which are used in the physical layer. The next is switch that you have just seen. Along with switch, there is one device is called as bridge. Rather, they are similar. The bridge is used basically to connect multiple LANs. And these devices, bridge and switch, are used in the data link layer. We'll next see a network layer, where a device called as router is used to route the packet arriving from one network process to some other network process on some different machine. So router is used in the network layer. Now there are different gateways. Gateways are also the devices used to connect different networks, but the difference between the bridges and gateways is that rather the bridges will be mostly concerning with the hardware, and the gateways will be concerning with the hardware and software. There will be managing the differences between the hardware and software. So they'll be basically communicating in the terms of the transport and the application layers. So gateways are there. So a packet that we'll see in the network layer topic here, the packet header is used, TCP header is used, and the ultimately user data will be there. That is collectively called as a packet, and a frame out of that will be generated by attaching the frame header, and the trailer may be having the CRC. Now this is what is called as the frame, which is there in the data link layer. So today we have seen the Ethernet and its types, classical Ethernet and fast Ethernet, and we have gone up to Gigabit Ethernet as well as 10 Gigabit Ethernet. So thank you.